Welcome everyone. In today's video, we're going to talk about continuity. The function f is defined to be continuous at x0 if the following three conditions holds. What are the conditions? First condition is fx0 is how to be defined. Limit of fx as x approaches to x0 will exist, and lastly, limit of fx as x approaches to x0 will be equal to fx0. In other words, limit of fx as x approaches to a value like a from the left side and limit of the fx as x approaches to a from the right side will be equal to fa. When this holds, when we can say this holds, we will say our fx is continuous at the point a. For example, fx is equal to x squared plus 1 is continuous at 2. Why? Because when I try to check the limit, x squared plus 1, I can just plug this in, right? So 2 squared plus 1 is 5. And f2, which is also 2 squared plus 1, is also 5. So therefore, these are equal, and I can say my function at 2 is continuous. For example, gx is equal to under the root of 4 minus x squared is not continuous at 3. Why? Because I will see that g3 is not defined, right? 4 minus 3 squared. So therefore, I'm seeing that g3 is not defined. Therefore, I am going to say this function is not continuous at 3. If one of the conditions fail, we will say f is discontinuous at x0. So we are saying that our gx is discontinuous at 3. Now let's look at fx is equal to 1 over x minus 2. Is fx continuous? At 2, of course. Is fx continuous at 2? When I look at the graph, I have two choices. I can look at the graph. If I have an empty value if I have an empty point at the graph, at that point we will say we don't have continuity. If there's jumping, we will again say there is no continuity. And at 2, I'm clearly seeing there is jumping. So therefore, by looking at the graph, I can say this function is discontinuous. Or what I can do is I can check f2. Is f2 equal to limit of the function at 2? F as x approaches to 2. 1 over 0, right? 2 minus 2, 0. So since this is not defined, we will say fx is discontinuous at 2. Fx equals to x squared minus 4 over x minus 2 is discontinuous at 2. Why? I don't have the graph this time, so I have to check the limit and the function. If one of the conditions fail, that's it for us. We will just say this is discontinuous at this point. X squared minus 4 is clearly 0 or 0 form, so therefore I can say that this continues at 2. Define function f as follows. Fx is equal to x squared if x is not equal to 2, is equal to 0 if x is equal to 2. Of course, we can check the continuity in piecewise functions too. After this video, we will have some examples and we will see other examples about piecewise functions and continuity and stuff. Is fx continuous at 2? First of all, what is my f2? When x is equal to 2, it's 0, right? So therefore f2 is 0. What is the limit of fx as x approaches to 2? We learned that we need to check the limit from the left and right when it's a piecewise function. It could be a jumping point, it could be anything, right? When I approach 2 from the left side, of course I'm not equal to 2, therefore I'm going to use the square one, so this is 4. And let's say, let's clear this part. When I approach 2 from the right side, again, I am not equal to 2, so therefore I'm going to use this one and it's equal to 4. These are not equal. So what is this telling me? This continues at 2. Let f be the function such that fx is equal to absolute value of x over x for all x is not equal to 0. Fx is discontinuous at 0. When I look at the graph, it's pretty easy to say there's no limit at 0, right? Or I can easily say this function is not defined at 0 because of the graph. In this problem, the graph is given to us, but even if it wasn't, I could just say f0 is 0 over 0. Therefore, there's no limit. There is no continuity. The function by itself is not defined. Because of the reasons I learned, this function is discontinuous at 0. Theorem. We will assume that f and g are continuous at x0. Then the following all of these conditions hold. F plus g, f minus g, f times g, f over g, c times f to f to the power of nth root to the nth root, f to the nth root is continuous at x0. All of these are also going to be continuous. We only showed a in this problem. You can show the others by yourself. It's real easy. Limit of fx plus gx as x approaches to x0. I want to show that this is continuous by saying fx and gx are continuous. I can write this as limit of fx as x approaches to x0 plus limit of gx as x approaches to x0. There's a little mistake here. x0. And I know that this is equal to fx0 because this is continuous, and I know this is continuous, so this is gx0. So therefore, I showed this limit is continuous. By doing the same steps, you can show the other the conditions of the other theorems as well. Every polynomial function is continuous. Another information we have here. And definition of continuity, the last thing we will talk about today. The thing is, in some majors, I think they don't give this. Maybe. And I didn't see this in some calculus books, but I still decided to give it because at least we will say we gave it. Definition of continuity is f is continuous at a point x is equal to a if for every epsilon greater than 0, there exists a delta greater than 0 such that absolute value of x minus a is lesser than delta whenever absolute value of fx minus fa is lesser than epsilon. We're not going to solve a problem about this in this video, but maybe we can in the future. I am still not sure who takes this, like in what measures they give it and in what measures they don't. So if your professor or your teacher never talked about it, just skip this part.